Radio telescopes help scientists explore the universe, but they also serve other purposes, such as satellite navigation and planetary defense. While satellite navigation is known by almost all as GPS, planetary defense is a more uncommonly known subject that has been progressively gaining attention over the past decade. What is planetary defense, and how is it possible? Find out on this episode of Beyond the Breakthrough, where we break down the latest developments in science and technology with help from the experts behind them. I'm your host, Kelsey Underwood. Before we get started, please note, the Green Bank Observatory and the National Radio Astronomy Observatory are facilities of the U.S. National Science Foundation, operated under cooperative agreement with Associated Universities Incorporated. The opinions expressed in this podcast do not necessarily represent those of the NSF, and the implementation of any radar system on these facilities would be subject to NSF review and approval. Now let's dive in. While radio astronomers often explore space objects that are up to billions of light years away, defense personnel use the same radio telescopes paired with radar technology to examine objects close to our planet or near-Earth objects, for instance, asteroids. One of the most famous asteroids known is Chicxulub, which collided with Earth around 66 million years ago and caused the extinction of dinosaurs. May sound familiar, right? However, this isn't the only asteroid that's ever impacted our planet. For example, an asteroid the size of a small building disintegrated about 20 kilometers above Chelyabinsk, Russia, in 2013. The explosion injured several people and damaged buildings as well. To prevent similar events in the future, the U.S. Space Force and other space organizations such as NASA and SpaceX have launched planetary defense programs where radar is commonly used to track these near-Earth objects.
I think that a lot of people, whenever they think about planetary defense, think that we are sending people out there to go do things like the Bruce Willis model, right? Go into the asteroid, taking the fight right to the asteroid. But a lot of what we do are from ground-based observations and trying to really figure out the problem using our instruments here on the ground. There's so much that you can do from antennas and telescopes on the ground that people just don't really fully realize.
If you've listened to our episode overviewing radio astronomy, then you likely recognize that voice. It's Will Armentrout, a scientist at the U.S. National Science Foundation's Green Bank Observatory and a Space Force officer in the United States Air Force. Will most certainly fits the bill of an expert guide through the topic of planetary defense. He's been with the Green Bank Observatory since he was a PhD student at West Virginia University, researching star formation regions using the Green Bank telescope and the Very Large Array. He went on to complete his postdoc research at the observatory and became an associate scientist in 2020. At the Green Bank Observatory, which is commonly referred to as GBO, Will wears many hats, including researcher, project scientist for the 20-meter telescope, workshop coordinator for student programs, intern mentor, and radar specialist.
I think it's a really fun job to be an astronomer at an observatory because you don't only have your research, you have the whole infrastructure of the observatory that you get to be a part of, and you get to help guide new instruments and new programs for the future of astronomy. So this is a great place for me, and I think you'll find the same story from a lot of the astronomers around Green Bank and the NRAO sites.
If Will isn't at the observatory during the workday, you can likely find him at the Air Force Base, working as a space operator. Over a 9-month period last year, Will completed his training, learning about the U.S. satellites in space, how to control them, and how to troubleshoot possible issues, such as effects from solar storms. While Will primarily examines galaxy formation at the observatory and near-Earth objects at the Air Force Base, his work at both institutions parallels each other.
In the Air Force world, there are antennas. In Green Bank, there are telescopes. But we're using a lot of the same technology. Just on the Air Force side, we're looking at things that are much closer. So we're looking at satellites largely and trying to take care of all of our national resources in that way. Whereas in Green Bank, we're looking at things back to, 14 billion years in the past, 14 billion light years away. So same technology, very different scales of things that we're looking at.
Founded as a department of the Air Force in 2019, the Space Force's mission is to secure our nation's interests in, from, and to space. As a military service, the Space Force's work differs from the work of a civilian agency such as NASA.
So if you think about launching satellites, launch vehicles, launching potentially in the future humans to space, NASA does all of the human launches, but Space Force and NASA work together in many ways as well, taking care of satellites that are there, taking a survey basically of all of the space debris also, because we have thousands of satellites in space and some of them have impacted each other in the past and left clouds of space debris. So the Space Force also takes care of monitoring that space debris and alerting different satellite companies or governments whenever some of that debris might impact some of their operations. So if there are bolts that they have been tracking that are going towards the International Space Station or something like that, they'll alert the astronauts, they'll alert NASA that this event could be coming. And in the past, they've sheltered in one of the return pods, for instance, waiting for that debris to pass.
Will's role in the Space Force is to monitor satellites and prevent issues such as jamming, which involves intentional interference with the signals transmitted by a satellite by sending out a strong disruptive signal on the same frequency, blocking the satellite's communications capabilities. Will analyzes jamming signals to understand how they function and how to counter them. Similar work is also done to counter the interference at Green Bank Observatory and other radio astronomy observatories. As GBO scientist Patrick Taylor mentioned in part 1 of our radar series, scientists at Green Bank Observatory have been working on the development of a new radar system, ngRADAR, which will use the 100-meter Green Bank telescope, or GBT, as the transmitter and the Very Long Baseline Array, or VLBA, as the initial receiver. In the future, the upcoming Next Generation Very Large Array, or NGVLA, will receive. The project is a collaboration between the U.S. National Science Foundation's National Radio Astronomy Observatory, NSF's Green Bank Observatory, and the aerospace and defense company Raytheon. If you missed Patrick's episode and you're unfamiliar with how radar works to detect and capture images of objects in space, I recommend taking a listen. You can find a link to his interview in the show notes of this episode. During a test run of the prototype for ngRADAR in 2021, scientists captured some of the best images of space ever taken from Earth, including the highest resolution image of the moon. In this image, over 1 billion pixels make up the 86-kilometer diameter of the Tycho crater. You can find this incredible shot linked in the show notes as well.
Some of what makes this an incredible system is that it's at a higher frequency than what most radar systems operate at. And so as you move up in frequency, your wavelength becomes smaller and you're able to have a better resolution. You can make out finer details on objects than with a low power or a low frequency system. So there's the strength of the wavelength, there's the strength of the power. This is a relatively high power system, and the more energy that you output, again, the better resolution you're able to get on objects.
While the technology of the new radar system on the GBT greatly contributes to its success, it couldn't perform as it does without its receiving counterpart.
We are receiving with currently the VLBA, in the future the NGVLA, and so we're leveraging the strengths of both of those instruments. The Green Bank telescope has a huge collecting area. In radar, I guess it's not a collecting area, it's a transmission area, but a huge area that we are able to leverage to make a very small beam on one of these objects that we're looking at. So we get awesome resolution, transmission resolution with the GBT. And then we use the VLBA that is spread across the country, can make, again, some of the best resolution images from anywhere on the Earth. It's a telescope that covers the size of a continent. And as you get instruments further apart, you get much, much, much better resolution. So we have the resolution benefits of using that interferometer that I think combine to make this an unparalleled instrument in the history of the world.
The VLBA is a 10-25-meter antenna system spanning from Mauna Kea, Hawaii to St. Croix in the U.S. Virgin Islands. By using two different telescopes, one for transmitting and one for receiving, scientists can record more data in a shorter amount of time.
The fact that we are using two different instruments means that we can continually transmit. So if you are transmitting and receiving with the same antenna, you are limited in how long you can transmit, because you basically have to send out a pulse of radio energy. Then you have to shift to a different instrument on that telescope before the light comes back to receive. The fact that we are using two telescopes means that we can just sit there and transmit with the GBT for as long as the object is up and receive with the VLBA or the ngVLA. And that means we don't have to constantly shift back and forth between transmit, receive, transmit, receive, transmit, receive, which is what some radar systems do. In this setup, it's called a bistatic system because you're using two antennas, one for transmit, one for receive. So you're able to observe for a lot longer with that kind of setup. My involvement with the radar project historically has been in our bistatic observations, and there's been a lot of great science from that. Things like measuring the spin rate of Venus, which we had no idea what it was until we did radar observations between Goldstone and the GBT.
Another key player in the success of ngRADAR's efforts, which may be unexpected by those outside the field, is optical astronomy observatories.
Asteroids are normally detected from optical telescopes. They will take these pictures of the sky, let's say one night, and then the next night they'll take another large picture of the sky. And if you subtract those two images, then you can see what has changed. So that's mostly how asteroids are detected, just from things changing between pictures from one night to a next in the optical. Asteroids aren't emitting their own light, but they're reflecting sunlight back to us. So the optical community will find these asteroids and then turn it over to the radio community to characterize. Because with optical telescopes, you can really just tell line of sight how the asteroids are moving. So you can see, okay, it's moving across this area of the sky. It's probably going roughly in this direction. But with radio telescopes, you're able to tell not just the direction on the sky, but the direction, how much it's coming towards you or away from you based on the Doppler shift of light.
So, how exactly will this ultra detailed technology benefit the Space Force and other planetary defense programs?
So, if an asteroid would be coming towards the Earth, we are able to characterize its orbit, tell what its motion is, if it might be on an impact trajectory with the Earth. And if we ever have something like the dinosaurs had, that came and impacted the Earth, with our radar technology, we would be able to tell well in advance that it was coming, and then hopefully put something together to try to push the asteroid away or do something else, so that we don't go the way of the dinosaurs.
The Double Asteroid Redirection Test Mission, also known as the DART mission, is a great example of what ngRADAR could assist with one day. As Will has said, NASA and the National Radio Astronomy Observatory facilities sometimes team up for certain projects, and this was one of those times. The DART mission was the first ever mission dedicated to investigating and demonstrating asteroid deflection by changing an asteroid's motion in space through kinetic impact with, you guessed it, a DART-like spacecraft. The asteroid of interest was Didymos and its moonlet Dimorphos.
So we weren't involved in the planning of the mission or actually sending the spacecraft up, but we were involved in seeing how that asteroid's movement changed after the NASA spacecraft hit into it. So the radar observations with Green Bank and with the Goldstone antenna out in California provided the first characterization of how much that asteroid changed trajectory. So NASA sent a spacecraft up. It impacted this little asteroid. There were actually two. It impacted the smaller of the two. And we found that it actually was a lot more effective in redirecting that asteroid than we expected to. There was a factor of a few times more momentum imparted, I believe, than what people had predicted. So that's really the world's first ever planetary protection mission, where we went out and saw how we would be able to push an asteroid away if we ever had something coming towards us, like what ended the dinosaurs, right? So it was an awesome thing to be able to be a part of. And the fact that our instruments were used were super special too.
In addition to naturally occurring space objects, the ngRADAR system will also have the capabilities to detect those that are man-made. Satellites, for instance, are placed in space to serve many purposes, including but not limited to communication, weather forecasting, and scientific research. As of November 2024, the United States has over 8,500 satellites in space. While modern satellites are designed to be highly resilient, malfunctions occasionally occur due to things such as space weather, collisions with debris, and technology failures. Malfunctions can result in terminated communication between a satellite and its operators, inhibiting tracking. ngRADAR would serve as the search and rescue team.
So sometimes you have that where systems malfunction, navigation malfunctions, and you need to be able to search for space objects. We would be able to presumably detect that satellite and be able to provide some information about where the satellite is back to the owners.
Understanding the location of space objects, both natural and man-made, also play a crucial role in protecting crewed space missions, which Will says ngRADAR could also contribute toward. Thinking back to how radar developed during World War II to detect enemy vessels and aircraft, it's fascinating to see it come full circle, providing protection in yet another way, among other uses in the field of planetary science. In December of last year, the ngRADAR team completed a third deployment of the prototype transmitter to exercise the end-to-end concept of operations for the radar system using the Green Bank telescope and the Very Long Baseline Array. What makes the Green Bank Observatory the perfect home for the ngRADAR project? Its unmatched expertise across the radio spectrum.
I think a lot of the expertise that you need to build this next generation radar system already lives within our community. And so this is an awesome place for it to be built, but also just the huge scale of our instruments. We already have either pre-existing large instruments like the Green Bank telescopes or plans to build these next generation instruments. And so the fact that they can be dual use for traditional astronomy and radar science, I think is a strength of NRAO and GBO and AUI taking on this project.
That concludes our episode with Will. I learned so much from our conversation and hope you learned something too. Will, thank you for taking the time to speak with me, and thank you for your service. If you would like to learn even more about ngRADAR, you can visit the project website at ngradar.nrao.edu. To learn more about Will's work specifically, you can visit his website, willarmentrout.com. Also, as I mentioned earlier, be sure to listen to Will's first interview to learn the basics of radio astronomy. You can find the episode link in the show notes. And last, if you would like to be notified about new Beyond the Breakthrough episodes and bonus content, be sure to subscribe wherever you listen, and consider leaving us a review while you're there to let us know how you're enjoying the podcast. Also, follow AUI at Discover AUI on Instagram and Associated Universities, Inc. on Facebook and LinkedIn to stay updated on all the latest breakthroughs at AUI. That's all for now. Thanks for tuning in, and I will see you next time.